Understanding turbulence makes sense to start from the simplest example: turbulence in incompressible fluid. Water is a typical example of the incompressible fluid. Indeed, to a certain extent, water can be considered as incompressible. From the first view, it might look counterintuitive, but to a good approximation, we can consider water as incompressible. Also, we choose water as the simplest example because water is a single component and homogeneous isotropic medium, so it does not contain any additional components which might complicate the consideration. The dynamics of continuous fluid medium is described by the well-known Navier-Stokes equation. In very general case of non-homogeneous anisotropic medium, this equation might look very complex. In our case of homogeneous and isotropic fluid medium, the Navier-Stokes equation look as follows. The evolution of turbulent motion is determined by the interplay and competition between convection and diffusion terms in the Navier-Stokes equation. Let's consider a situation where homogeneous and laminar flow encounters an obstacle on the way. This obstacle disturbs the homogeneous velocity distribution, particularly because there is no driven flow upstreams in the shadow of the obstacle. Within this shadow region, the dynamics of the flow is determined by the interplay and competition between diffusion and convection transport mechanisms. Diffusion is a collisional process which leads to the gradual spread and smoothing of inhomogeneities, such, for example, as an unhomogeneous velocity distribution. Unlike convection, diffusion does not rely on direct particle transport. Instead, it depends on random particle movement resulting in mixing without the need for direct bulk motion. This intrinsic characteristic distinguishes diffusion from convection. In diffusion, there is no necessity for flow within the medium. A classic example of diffusion is heat diffusion throughout a home's wall from inside to the outside, leading to thermal loss. Notably, there is no flow within the wall, causing this heat transfer. The essence of diffusion lies in particle random motion, enabling mixing or mass transport independent of direct bulk motion or flows. Discussion surrounding the interplay of diffusion and convective transport in Navier-Stokes equation can be the subject of some confusion because we are essentially describing the transport of velocity, which is a case of transport of transport. This can lead to misunderstanding. The key conceptual difference between the convective and diffusive terms lies in their relationship with fluid velocity. The convective term directly involves the fluid velocity, while the diffusive term does not. Instead, the diffusive term is not linked internally to bulk motion. It's primarily associated with statistical random motion rather than the fluid's overall movement. Consequently, diffusion leads to the spreading of physical quantity without requiring bulk fluid flows. Note, however, that it does not matter what quantity spreads out. It can be also scalar quantity, like temperature or density, with corresponding diffusion term, which might look like this. But we can also talk about the diffusion of the velocity. In other words, diffusion of the fluid flow. The important and common here is the Laplace operator, which determines the spreading. Contrary to the diffusion, the convective transport is directly related to the fluid motion, since velocity directly present in the convective term. It describes the transport caused by the bulk flow, similar to the convective heat transport in the boiling water. Again, the same as with the diffusive term, it can be a scalar quantity like temperature or density, with the corresponding convective terms like this. But it can also be a convective transport of the fluid velocity or fluid flow. The important and common here is this operator, determining the convective motion of the quantity. The interplay between these two transport mechanisms, diffusive and convective mechanisms, dictates the dynamics of the fluid flow upon encountering obstacle or spatial inhomogeneities. Diffusive transport tends to flatten and smooth out any spatial irregularities, whereas convective transport leads to the formation of enfilamentation and fragmentation in the transported fluid. This convective behavior is often characterized as turbulent behavior. The illustration below shows the emergence of sharp gradients. Let's consider the development of turbulence using a specific example, the interaction of two eddies. Eddy is a swirling of fluid created within the fluid in a turbulent flow regime. This example demonstrates how ordered and symmetric motion gradually breaks down into disordered, chaotic turbulent motion. The video below shows a result of numerical modeling of the Navier-Stokes equation. A crucial parameter determining the transition to turbulent motion is the viscosity coefficient. Viscosity defines the relative role of diffusion in the Navier-Stokes equation compared to the convection term. The diffusion coefficient, that is the coefficient in the Navier-Stokes equation. This coefficient. The smaller it is, the less important the diffusion transport in the motion. In our example, we will consider two cases. We will compare two cases. An example of relatively weak diffusion and an example of stronger diffusion. In both cases, at the initial moment, we have two interacting vortices. The initial condition for both cases are the same. However, the process of their interaction differs significantly. We will begin our discussion with the case of weaker diffusion. In the video below, you can see how interacting vortices gradually decay into separate smaller fragments. This process of fragmentation and formation of smaller structures essentially runs continuously. Large structures break down into smaller ones. They in turn break down into even smaller ones, and so on. This process of decay of two vortices looks fundamentally different in the case of increased viscosity, which means enhanced diffusion.